Okay, hey everyone, welcome. This is our talk on profiling. We're going to be talking about a lot of different profiling tools out there and discussing kind of the background and like some information you need to know about profilers before you can be most effective for using them. I am Shana Matthews. I'm a developer advocate at Sentry. In my past, I've been a developer advocate a lot and also a software engineer. Indragie?
Hey, I'm Indragie. I'm a director of engineering at Sentry, and my teams work on session replay, which launched earlier this year, and also profiling, which we'll be talking to you about today.
We're probably not going to really talk about Sentry too much, like at all, during this presentation, but we do have a booth, and we'd be delighted to talk to you more about Sentry, so please come find us after this or at our booth, which we'll be hanging out at this evening and like all day tomorrow and the next day. Cool. Okay, so yeah, like I said, I'm going to start this out by doing like a background on profiling and kind of giving you more conceptual information about different kinds of profilers, and then Indragie will take over in the second half and do a demo to show some of the stuff more hands-on. Great. So I like to be interactive. I won't ask you questions, really, don't worry. But before we start, I kind of like to get a sense of how familiar people are with profiling. So please raise your hand for me if you're like what you would consider novice at profiling. Like, don't really know what it is, you just played around with it a little. Okay, cool. Maybe like more of an intermediate level, like you use them, but you're not an expert. Okay, cool. And like, raise your hand if you are an expert at profiling. Okay, ask him the questions. We'll be directing questions to him. No, just kidding. Okay, cool. And so obviously this is Python, so we're going to talk about some Python-specific profiling tools. So how many people have actually used Python's profile or cProfile? Good, lots of you. Okay, that's great. We'll definitely be talking about that, but talking about some other tools as well. Okay, last one I promise. How many people have used continuous profiling tools? So like AWS and GCP have versions. Okay, a couple people. Cool, we're gonna talk about those a little bit as well. Great, so I'm gonna start from like the very basics, but we won't spend too much time on the super simple stuff. But what is a profiler? So a profiler is a dynamic analysis tool. So this means that it works while your code is running, and this is really in contrast to static analysis tools. So really common static analysis tools you're probably familiar with would be things like code coverage or things that can look at your code and like pick out potential security flaws. So those are things that can just look at your code even though it's not running and give you this information. Profilers have to be running while your code is running, otherwise it can't really tell you anything. There are so many different types of profilers out there. There's it's like anything that you want to measure about your code, you can pretty much get a profiler to do it. But the most common ones by far would be memory profilers and CPU profilers. We're really going to exclusively talk about CPU profilers today, but just like earlier in this room, it was cool. There was someone talking about, at the Bloomberg talk, they're talking about memory, that memory profiler. So go talk to them if you want to talk about memory profilers. Cool. So even within CPU profilers, there's actually like a lot of variation in how they work. And the way that they are designed really impacts what they're most useful for and like what they're most effective at measuring. Okay, and we are now going to do a little bit of history of profiling. I really like learning about the history of computing, and I think it's so helpful to understand a little bit of the background about these things. Things just build upon each other, and technology just gets more complicated, so it's good to understand where things come from to know where we're at. Cool, so profilers have actually been around since the 70s, which is crazy to me. The first ones were made by IBM, and they basically worked by using timer interrupts and stopping the system and recording the register. So by doing this, it was kind of by definition a sampling profiler, and don't worry if you don't know what that really means yet. We'll be talking a lot more about what that means later on in the talk. And then the first profiler that shipped on Unix was just called prof. All it could really give you was just a printout of all the different functions that it saw and how long it saw them running for, which was like really helpful for them at the time, but obviously now we have a lot better tools. In 1982, the first Unix profiler that could actually give you a call graph shipped. So that was very revolutionary at the time. And the call graph, if you have used like Python profilers, are those like pretty colorful graphs. They mostly look like a tree that show you the hot code paths. I don't know if they were really that colorful back in 1982 when these were happening, but that's when the first one showed up. Cool. So back then, profilers were like mostly used on profiling compilers, which that's cool because compilers were like some of the most computationally intensive things happening at the time. But kind of for a while, there weren't many breakthroughs for a little bit. There was this Atom paper, which I have listed here. I think that's neat because the Atom paper was really about figuring out how to make your program's code modify itself. So this was used for a lot of things, but they also like implemented this in compilers. So instead of having to run the compiler as a completely separate thing, your profile or your code could actually profile itself, which is what we do very commonly now. This was actually called instrumentation in this paper, which I think is funny because now we all use the term instrumentation very freely, and it's like a very obvious concept, but this was like when it was decided to be a new term. All right, and then pretty soon after that, in 1997, actually, the term continuous profiling came into the lexicon. This was another paper, and it was about how you could run profiling continuously on just one machine. So this was the first time like continuous profiling was actually happening. It still was probably not that good at the time. It was doing statistical profiling again, and it was really exciting because you could save your profiles on the same disk and run this all the time on one machine. It maybe wasn't very accurate at the time still, but it was functional, so that's cool. And then sometime in this timeline, deterministic profilers showed up. I really tried to find when deterministic profilers first started to be discussed, but I couldn't. So if you know, I would love to hear more about that. Again, deterministic profilers are like the flip side of sampling, but we'll talk about that a lot more in a little bit. Great. Okay, the next really big thing on here was Google's Google-wide profiling paper. So this was a big expansion of the idea of continuous profiling. This came out in 2010 when Google decided published about how they had decided to profile like all of their machines across data centers. So this is taking continuous profiling from running on one machine to running on like thousands and thousands and thousands. Obviously, for Google to do this, they had to make sure they had a really low overhead, and they were able to get pretty high accuracy. The tool that they used for this was called cProfile, which I don't actually know that much about, but if you want to look at it more. Yeah, and Google obviously cared about this because they were doing this in their data centers, and it was a massive cost savings if they could shave off even a little bit of time to these CPU-intensive processes. So that's why they cared. And now that we're all running things in the cloud all the time across data centers, we're all starting to care about this. So there's kind of been breakthroughs every 10 years or so, so maybe not so surprising that now in the 2020s, we're seeing an explosion of continuous profiling tools. And a lot of these are based on open source profilers that have just gradually been improving over the years. So much thanks to all the maintainers out there. Cool. I'm going to take a sec also to compare profiling to the traditional like 3 pillars of observability. I don't know if people here are like really into observability. I definitely wasn't before joining Sentry. So I'll just talk a little bit about what they are and how profiling is different. So tracing is one of the pillars. It's very often referred to as distributed tracing. Tracing is basically tracking a request as it moves through a system, and if it's moving through multiple systems, it's distributed. Distributed tracing is like really helpful. It gives you a lot of information, and it can also give you information about the timing of those requests. So it's very helpful in performance, but it's useful for a lot of other things too. Tracing is great because it can give you information about external parts of your code that might be slow. So if you're calling services that are slow or your database is slow, you can really see that information by looking at your tracing data. However, it is not that great at telling you why your own code is slow unless you want to go in and add a whole bunch of instrumentation inside your own code, which some people do that, and that's great, but it's a little time-consuming and burdensome. So logging. Hopefully everyone is familiar with logging. Logs are very manual. We all know that. They can be used for performance, but are also just like totally useful for debugging stuff, even though it can be a pain to dig through them sometimes. I don't think that profiling can like compete with logging in any way. It's just like another tool to use on top of logging. So sorry, you're gonna have to keep digging through your logs a lot. And then finally, metrics. So metrics are just numeric measurements, and you collect them like continuously as your system is running. Metrics are like just numbers, so they are really efficient to store, unlike logs. but they're not so great for giving you any information about why things are happening. They're super awesome for letting you know that something is going wrong, but if you need to actually go figure out why that's happening and fix it, your metrics aren't going to do anything for you. Okay, so profiling. I definitely think profiling is like complementary to almost all of these. I think there are certain use cases where profiling can like replace or like maybe could start to replace tracing, but that's maybe for another person's talk. Profiling is really good for doing exactly what metrics can't, which is showing you where things are going wrong in your own code. So if something like bad is happening, it can pretty much get you like down to the line number of where that slowdown is happening. And you don't have to like dig around for it. Yeah. Cool. So now we will finally talk about deterministic versus sampling profilers, which I've been like previewing over and over again. At a really, really high level, deterministic profilers are really focused on precise function timing information. So every time that a function starts or ends or an exception happens, your deterministic profiler takes note of that. They also definitely have a higher performance overhead. So doing this for every single function, start and end, takes up a lot of overhead. This slide says like more than 15% overhead, but in reality, it can be a lot more than 15% overhead. It can be like 200%, like 2 times, 3 times, more than that even. On the other hand, at a super high level, sampling profilers they compromise by giving you less precise information with a much lower performance overhead. So how does that work? So I said that these deterministic profilers basically track every time that a function starts and every time that it ends and every time an exception happens, but that's not really on here. And so, yeah, this is that diagram, and that's the top part. And then on the bottom part is a discussion of how sampling profilers work. So what you can see is that on these dotted lines, that's basically where the sampling profiler is taking a snapshot of your call stack. So instead of doing that all the time, it's just doing that on a regular basis. Yeah, this is really great because it means that the overhead is constant. So on that top diagram, the more function calls you have, the more overhead that the profiler is going to add. And that can be frustrating and also like mess up your data. On the bottom, like you have a very consistent amount of time that you're going to spend grabbing samples. So the profiler's overhead is both lower and more consistent. Cool. Okay, so this is just a little bit more about how the sampling profiler works. So I said it's like a little bit less accurate, which is true, but they're like very fancy and they collect so many samples now that we pretty much don't even need to think about them as being too much less accurate. So this is basically how that would work. So we had this dotted line showing when we were taking snapshots of the call stack. Imagine we took one at 0 milliseconds, which would be sample 1, and we see we have ABC, that's our call stack. And then we take another snapshot at 10 milliseconds, and only A and B are on the call stack. So these are our 2 samples, and really, really, really roughly here, we can see that, we can say that C took about 10 milliseconds. Obviously, actual sampling profilers are taking many more samples than this and have a lot more data, so they can use fancy math to be really accurate about how long things actually took. Wonderful. Okay, so that's sampling versus deterministic profilers. Now we're going to talk a little bit about profiling locally versus in production. It sounds like a lot of you are quite familiar with profiling locally, which is probably what you're doing with your Python built-in profiling tools on your computer. Yeah, local profiling usually uses these deterministic profilers. So Python cProfile and Profile are both deterministic. Profiling locally is not really representative of what's happening in the real world, though. So the more complicated your system gets, the more external things it's calling, the less similar what's happening on your dev box is to what's actually happening and what your users are seeing. So sampling in production is really helpful for a more complicated or like cloud-based product. Yeah, so in production, you'd usually use a sampling profiler because you really don't want to give your code any more overhead when your users are actually using it. And yeah, and you get a whole bunch more real-world information. Okay, let's talk a little bit about visualizing profile data. So hopefully a lot of people here recognize this. This would be the output of like if you ran cProfile on your computer and then you put it into gprof to dot. This is like the kind of thing that you'd get out of it. Yeah, these are like called call graph visualizations, and these are actually the ones that were invented back in like 1982 or whatever. So these have been around for a really long time. They're still very useful. There's honestly not much wrong with that. We have new ones, and like we'll talk about new visualization types, but just this is really quite intuitive. It uses colors here to tell us where the slow parts of our code are, and this nice diagram shows us our like what ran after what. So you can just look at this and see where a hot, warm-colored, hot code path is, and that's where you can start investigating. But like I said, a lot of time has passed since those were invented. We definitely have new, better ways of visualizing profiling data. So one of those ways are flamegraphs. This is an example flame graph. Flame graphs were invented by this guy, Brandon Gregg, in like 2016, I think, when he was working at Netflix. So these have also been around for a while, but at least I wasn't familiar with them personally as a dev until pretty recently. Yeah, so his idea for these were to make it easier to interpret profiling data. I think that's maybe a little bit subjective. I don't know, when I look at this, I don't think anything about this looks easier to understand than just the call graph. But we're going to talk a little bit about what the parts of this are so that you can get a little bit more familiar, and I'll give you some like tips for interpreting these, although it's definitely a skill that you have to build up over time. So yeah, this is a flame graph, and first of all, the reason why it's called a flame graph is because it looks like flames. It's really not that deep. It's red, and there's little licks that look kind of like fire coming off of it. What you're actually looking at is the stack traces of a profile here. So a stack trace is a column of rectangles, and each rectangle you're seeing on there represents one function or a stack frame. So that's like what the y-axis shows. It shows the stack depth. So anything that's at the top is basically what was on the CPU when a profile was collected. And then anything under that is that function's parent. Really importantly here, and it's not necessarily intuitive, the x-axis does not show time. It doesn't show time. The x-axis kind of like doesn't really show much. It's just a good grouping of the frames. So the way that things are organized left to right here is actually almost always alphabetically by the function name. And then if two rectangles next together have the same function name, they get combined into one bigger rectangle. So that's what you're seeing here. Yeah, they just get merged together. And then the width of these rectangles up here shows the frequency with which that function was seen in the sample data. So that's kind of a really precise thing, and I want to emphasize it. The wider the rectangle, the more often that function showed up. It doesn't mean that that function takes longer necessarily. It just means it was seen more often. It often means that it was slower. That's not exactly what it means. It could just be called like 5 million times, and it would show up the same way. And yeah, the colors here, while it's very colorful and kind of pretty to look at, the colors are actually basically meaningless. They're just random colors that were picked that looked nice. Brendan liked this color scheme, I guess, and everyone's stuck with it since. Yeah, they're literally just different colors to help your eye differentiate them. But different kind of people have built upon this and used colors in a way that's more like informational rather than just cool looking. Okay. So we kind of know what the parts of a flame graph mean, but how do you actually look at one of these flame graphs and get any information about where your code is slow? It's not obvious. So like I said, it is a skill, and the more you do it, the kind of more you'll just intuitively understand what flame graphs are telling you, especially when it's your code base. But some like tips that you can try to apply if you're getting started, obvious stuff would be look for large plateaus along the top edge. So if there's a big function with a big exposed top edge, that means that function was running really frequently on the CPU. So in this example, we can see that our function g, it's the widest thing on the top. D, which is it's like grandparent, is wider overall, but like the exposed top edge on D is shorter than G. So we would be more suspicious of G of taking a long time. Cool. Oh yeah, and then also like, C and B are like more parents. They don't have any exposed edge at all, so they were not really taking any time. A couple other things you can do. You can read top down to see ancestry. We've kind of covered that, so I think that's obvious. But yeah, you can scan down and see who called what. Or you could kind of look at this and read bottom up to get more of a big picture view of how your code flow is happening. Yeah, and then obviously look for wide function boxes. So our big boys here. We can see B on this code path was called about like 4 times more than H. So big, wide function boxes are suspicious, and you'd want to start looking at them to maybe understand if that's a long-running function. So I don't know. Is it reasonable that B is taking 4 times longer than H? I'm not sure. These are just boxes that were drawn. It's not real code. But you might know that about your own code, and that's what's important. The last thing that's kind of interesting that you can look at here are like big forks. So we have 2 big forks here. We have like the B fork and the H fork. So again, we maybe want to understand why is our code forking. So it could be something really obvious, like there's a conditional in A. It's like an if statement. If one thing B, if the other H. But it might not be that. It might actually be that something in A is being processed in 2 stages. Like maybe first it has to go through the B stage, and then it goes through the H stage. So yeah, just another thing to help you understand how your code is working and point you in the right direction when you're trying to find problems. Cool. Okay. Flame graphs versus flame charts. This is like a lot of the same looking stuff on one slide, so I'm going to try to explain it the best I can. First of all, flame graphs and flame charts are very commonly used interchangeably, and they're actually different. They're different data visualizations. They're specialized in different ways and are like better or worse for different kinds of tasks. Let me check. Okay, so basically what we're seeing here is a flame graph on the left and a flame chart on the right. And don't stress out. The flame graph here is flipped upside down. So flame graphs can be like pointy parts up or pointy parts down. It's the same thing. Some people like it one way, some people like it the other. But this is showing a flame graph and a flame chart for the same program. It's actually Fibonacci, so it's not that interesting, but you guys can't read the function names anyway, I'm sure, especially in the back. So it's not that big of a deal. The big difference between flame charts and flame graphs is that flame charts actually do show time on the x-axis. So this is really more intuitive in a lot of ways. Instead of just showing how frequently a function was being called, it really does show how long that function was running for. And it can be more approachable if you're just getting started with these types of visualizations. Yeah, otherwise the relationship of like parent-child, it's all the same. So one other interesting thing about these in particular, these were pulled from Sentry. We are using color meaningful here. So you'll see it's not just a random rainbow of reds. Here we have system calls in red and our own application calls in blue. And this is helpful so you know where to focus. Like obviously you're not going to make the system calls speed up at all. So just focus on your own. There are other possible ways that you can color code these. Some useful ones would be by package. So you could color code your functions by package, or you could color code the functions by frequency with which they were called. All of those might be more helpful ways of using color other than just randomly. Cool. Okay. Oh yeah, I was going to say flame charts were based on flame graphs, so they came second, and they were made by Google, but I think a lot of people actually prefer flame charts. I don't know. They're somewhat more common these days in my experience. Great. Okay, that's a big profiling primer. I hope you absorbed every single ounce of information. Indragie is going to come up now, and he's going to run through some hands-on examples of using different profiling tools. Come on up.
All right, thanks, Shana. So let me switch over to my other workspace. So the first thing I want to show you is the examples app that we're going to use for the rest of this workshop. It's extremely simple. So what we have here is a iterative implementation of the Fibonacci. So we're actually sticking with the Fibonacci stuff from the previous slide. And we're doing it iteratively instead of recursively because of Python's sort of like recursive depth limit. It makes it a little bit easier to get into this. So the Fibonacci sequence is the fib function there, and then we have a Flask server that just wraps it. There's a single endpoint. You hit the endpoint with the Fibonacci number you want, and then it computes the Fibonacci value, and it returns a response. So really simple, really easy to grok. So I'm going to come back to this, but first let's take a look at the documentation here. So Shana mentioned cProfile and Profile, and many of you raised your hands when she asked if people had used them, so you're probably very familiar with this. One thing I want to note is the distinction between the two. So they implement the exact same interface. cProfile is a little different in that it's implemented in C as a native extension, and so the reason for that is overhead has more reasonable performance overhead. Profile is implemented in pure Python, so it's more extensible than the C implementation, but it does come with the cost of significantly higher overhead. So for the purposes of this demo, I'm just going to stick with cProfile, and we'll kind of just try it and see how it works. So going back to my code, there's two ways you can invoke cProfile. So you can actually just do it by passing -m cProfile as a command line argument to Python, which will just run your script with cProfile attached. Or you can actually use the API directly. So I have a second version of this code that uses the cProfile API directly. So here, I'm wrapping my main function with a call to profiler.run call, which will essentially enable profiling, run that function, and then disable profiling when it finishes. And then after main exits, we're just going to create a stats object, and then we're going to dump the stats to the console. So let's take a look at what happens when I run this right now. So what I'm going to do is I'm just going to run my Flask fib cProfile script. It'll start the Flask server, and then I'm going to hit it with a request so that it computes a Fibonacci value, and like a sufficiently high sort of value, 300,000, so it takes a little bit of time. So you can see here, it printed the value, which is crazy long. We received a request, and then if we exit the process, you can see here it printed the output of cProfile. So I'm going to scroll to the top here, and you'll notice a couple things. So first of all, random listing order was used, so the ordering of the stuff in this table doesn't have any meaning. And then second, you'll notice that it's a little bit harder to parse here because we have these really long directory paths in the way. So you can see like the functions at the end, like list comprehensions and stuff, but a lot of it is this prefix. So we can make this a little bit easier to parse by doing two things. One is we can strip the directory paths, and then we can sort the statistics by something meaningful. So I'm going to sort, in this case, by the cumulative time. So save that change. We're going to try this again. And immediately here, you can see that the output is a lot nicer. So you're not getting those crazy long file paths. And then if I scroll to the top here again, this time it's ordered by cumulative time. And then we can see here that the function with the most cumulative time here is at the top. Something interesting you'll note here is we're not even seeing the Fibonacci function. So we'd expect this to actually take most of the time here. What we're seeing here is that the main function, which just starts the server, that's the one that has taking 4.3 seconds. And so the key thing to learn about cProfile from this example is that cProfile does not profile all threads in an application by default. So we started cProfile in the main thread, and so it only captured a profile for the main thread, whereas Flask will spin up additional threads to handle requests. And so the way to do this manually would be you need to set up, start cProfile on each request handling thread, end it when the request starts and ends, and there's a little bit of like manual work you have to do there to get it to actually show you the profiling data for what you're looking for, which is what took the longest when serving the request. But for Flask in particular, there is an easier way to do this. So if we go back here, Flask's WSGI server has a built-in middleware that does exactly what we want. And so it profiles each request with the cProfile module. So you just add this middleware, give it a path to where you want it to dump the profile output. You can add some other arguments like the sort order and so on, and it'll just profile all the requests for you. So we'll take a look and try that next. So here I have a second variation of the same server, except this time instead of starting cProfile myself. I'm just adding the profiler middleware and dumping it into this directory. And I've used this, this time sort order. So if I run this one, and then I'll run a request, you can see here it actually outputs the dump for each request as you send them. So if I go up here to the top, you'll notice the fib function now actually is at the very top of the list. So you can be sure that this is actually profiling the request because you see fib with the largest total time here at the top of the list. So that's sort of how you would use cProfile with a Flask setup. If you're using Django or some other framework, there's probably similar middleware, but this is sort of like one easy way to do it. So the next problem I'm going to try to address is the fact that this output here in this table is very difficult to parse. So if you're just looking for like the first function or two, this is probably good enough. But if you want to kind of assess the data more comprehensively, there's different ways to do that. So Shana already showed an example of a call visualization graph, and so we'll do that next. We'll generate one of those for this profiling data. So one of the tools that we can use to do this is called cProfile. So this is a script that takes in profiling data from a bunch of different types of profiling file formats. So Python's format is one of them, but it takes in other common profile formats, and then it outputs a dot graph. So you can basically take this output, pipe it into the dot tool, and then generate a visualization of your choice. So what I'm going to do here is I'm going to quit this. So I have this profile file that was generated here. So this was created by the profiler middleware. So what I'm going to do is I will run cProfile, give it the path to my profile, and then I will pipe that into the dot command to generate, oops, mistake. So I have to pass in a format. So this is the pstats format, which is the format that Python outputs in. And then it's outputted this PNG file. So if I look at this, actually maybe I'll want to show this in Finder and open it up. So you can see here, all of that table data has been condensed into an extremely simple visualization where you can see that the fib function was called here. It's about 80% of the runtime. And we can see that it calls this like append function on list like a whole bunch of times, which is because we're appending to this sequence here. So that's one way to visualize the data. The other way to do it is there's a tool called Tuna, which is lesser known. But this one sort of renders it in more of like a call tree representation that looks like this. So instead of a dot graph, you're rendering the same data with a call tree instead. One of the key limitations to note here, not of Tuna, but of cProfile and Profile in general, is they don't contain complete call tree information. So for each function, it stores the information about the immediate parent, but not information about every possible path that parent can take to call the child. So if there's, you're calling function C from function A, maybe it goes through B in some cases, maybe it goes through D in other cases, you cannot distinguish between those two cases in the output data. And so what it's actually rendering is, it's sort of a best effort of what it knows. And if you look at this README, it'll give you more of like a contrived example of how that limitation works. But for our purposes, like this isn't that relevant, so we can go ahead and just use it. So I'll pass in the path to the same profile output into Tuna, and it'll start a server and render this page, which shows me the same data that I was looking at in the call graph visualization, which is that the fib function here takes 1.47 seconds. So that's sort of the summary of the cProfile part of this. So in short, like cProfile, deterministic profiler, it's great for local profiling, and maybe not as suitable for production profiling because of the higher sort of overhead of deterministic profiling. But it's sort of a great way to get it, like a first look at how your application performs. And so now I'm going to go into some different profiling tools that are used more in production because they have sort of different performance trade-offs. So one of them is PySpy. So there's a couple interesting things about PySpy. One, it's a sampling profiler, and they actually document it's extremely low overhead. It's written in Rust for performance reasons, and most notably, it doesn't run in the same process as the profiled Python program. So in addition to the distinction between sampling and deterministic, you also have this decision that profilers make to run either in process or out of process. There's trade-offs to that. So if you're running in process, it's easy. You don't have to spawn a separate process. You don't have to use elevated privileges. You might be running in an environment that's highly constrained where you don't have control over, adding an agent or whatever. So that it makes it easier to integrate, but then the downside is that it is running in the same process. So if something goes wrong, it's more prone to breakage. It can crash a process. Whereas the out-of-process profilers, they run outside, so they're more safe, can be more performant, but of course, in some cases, they require elevated permissions to invoke the Python process from outside. So in this case, this is a out-of-process profiler, and it's a sampling profiler. And you can see here like a visualization of the same kind of flame graph that Shana mentioned earlier. Another option is PyInstrument, which again is another sampling profiler. This one is different in that it is an in-process profiler. So if you go here, there's actually an example. You can just invoke the profiler directly in your code, so you can like profile around a particular section of code and things like that. So you get like sort of like more like in-process control over how the profiler runs. And it's similarly low overhead because it is a sampling profiler. And then the last example that I wanted to kind of show before I go into more demo stuff is Austin, which again is a sampling profiler. This one also runs out of process. It also supports memory profiling, which the other ones don't. And it's just another option. It's also written in C. So yeah, anyway, there's lots of options for this. One read that I would recommend later on, if you're interested in sort of like comparing and contrasting these options more in depth, is this article, a survey of open source Python profilers. So this kind of a medium length write-up about the built-in Python profilers, various open source options, PyInstrument, PySpy, and Austin, which we just looked at here. So this will compare them more in depth. I don't have time to get into all of the reasoning described here, so this is sort of just an extra thing you can read later. For this demo, I'm just going to pick one of them. So I'm going to pick PySpy, and we'll run with PySpy and see what it does and how it compares to cProfile. So for the purposes of running under PySpy, I'm just going to go back to like the original script. So this is the Flask fib script. Oops, I'll just open that here. And the first thing I'm going to do is I'm going to invoke PySpy to generate an SVG version of the flame graph. So if I run this, oops. All right, cool. So now the server's running. I'll send a request again. And then it'll just create an SVG. So this is kind of interactive. Like you can hover over each of the frames and see the number of samples that were registered for each of those functions. And you can see pretty clearly here that it is properly profiling our request handling thread, because you see the fib call here with 155 samples, or sort of 75.9% of the total runtime of the profile. Sorry? Zoom in, yeah, sorry, yeah. Good point. Yeah, there you go. So this is what I was pointing out earlier. So you can see at the top here, like when I hover over the function, it shows 155 samples, 75.9%. And then above this, you can see all the parent stuff. So this is just the WSGI stuff. All of the WSGI server internals are all here. So this visualization is cool, but like Shana mentioned, there's two ways to look at this data. One is flame graph, which shows this. Basically, it's just the frequency information of how often something was called, or how often a sample of one of these functions showed up in the profile. And then the other one is a flame chart, which is it shows the duration on the x-axis, so you can kind of more easily understand how long something actually took. And so this flame graph visualization doesn't do that, but there's an alternative visualization that does. And we're going to use a different tool for doing that. So for anyone who hasn't heard of it, there's a tool called SpeedScope, which is fully open source. It's an open source WebGL-based flame chart and flame graph renderer. So it supports a whole bunch of different file formats. You can import those directly into the tool, or you can output your profiling data in SpeedScope's own file format and then render it with the tool. So if I just click into the example profile here, you can see this is a pretty involved flame chart. Or it's the flame graph, actually. You see this is the frequency on the x-axis, I think. This is in Python. This is just a random sort of profiling example, so you can see how like quickly it zooms and pans and stuff. It's like really good for looking at really detailed profiles. And it turns out that PySpy can generate this format directly. And so I'm going to go back to the code here, and I'm going to run PySpy with a format argument that tells it to output in the speed scope format. So if I do this, and then I send a request, I'm actually going to send a couple requests for this one. I'll just do like 3 with different values of n, so you can see more data show up. I'll do 3 to 1,000, and then here, you can see it wrote the speed scope file to profile.json and captured 295 samples. So I go back and then I import the profile.json into this tool. And you can see here very clearly my 3 fib functions. The first one that was the longest, second one, and then the third one. And so this also gives you the time on the x-axis. You can see here actually the units, they're in milliseconds and seconds. So from here, you can directly see that this took 1.43 seconds instead of looking at the flame graph, which just gives you a frequency. So this is a bit of a nicer way to look at it. The other benefit that this gives you is it does capture all threads in the same profile. So if I wanted to go and see what the main thread was doing, which was not that interesting because all it's doing is just running the server, you can switch over and see that, which you couldn't with the flame graph, because the flame graph aggregates the data from every thread into a single aggregate, whereas this separates them by thread. Yeah, so that's a little bit about PySpy. The other profilers, PyInstrument and Austin, they work very similarly to this. They can output some of the same formats. So regardless of which one you use, you can get the same experience. And the choice of which one you might want to use kind of depends on your specific production use case. So we talked a lot about sort of performance trade-offs and performance kind of overhead of various types of profilers. So the next topic that I wanted to cover is a little bit on overhead measurement and kind of quantifying what we say when we have a high overhead profiler. So what I'm going to do is I'm going to benchmark a bunch of these scenarios using Hyperfine, which is a benchmarking tool. And so the first benchmark that I'm going to run is a baseline, so no profiling at all with cProfile. And I'm just going to use a kind of shorter version of the same code. It's just the Fibonacci function with no Flask because we don't want it to be interactive when running the benchmark. So this is just a benchmark that runs fib directly and sees how long it takes. So I'm going to run Hyperfine. The first argument is just the base case, and then the second argument is with cProfile by passing -m cProfile. And I'm giving it one warm-up run just to warm the caches because that can impact the accuracy of the results. So it's going to run a bunch of iterations of this and kind of give you the difference with some error bars. So we can see here there's exactly 15% overhead from running cProfile on this script. So compared to no profiling, cProfile adds 15% overhead. We mentioned earlier deterministic profilers, their sort of overhead can increase depending on the number of function calls. So even though in this case it is 15%, you might see drastically different results depending on the particular workload. So 15% actually is not too bad. And then going back to the whole cProfile versus profile thing, they mentioned the docs that the profile version, the pure Python implementation, takes it's significantly higher overhead because it's written in Python. So we can actually try and validate that. So we're going to run the exact same benchmark, except this time using profile instead of cProfile, compared to the no profiling baseline. All right, so this one, you can pretty clearly see this is 106% overhead. So it's an order of magnitude more overhead than the C-based implementation. So this is an example of the kind of performance overhead you can sort of see from certain deterministic profiling tools that are not intended for a production use case. So this is still probably perfectly fine to use for local debugging, but you would never want to launch something that has 100% plus overhead in production. And then we can also now try PySpy. And there's two variations of PySpy that I want to try here. So We mentioned that for sampling profilers, we have a profiler that collects a snapshot of the stack at particular intervals. So the interval is essentially the profiling frequency. So a typical profiling frequency to use in production is something like 100 hertz. And so that means you're capturing the call stack 100 times a second, which means that you get 10 millisecond resolution on your durations. So if a function takes less than 10 milliseconds to run, that resolution is not significant enough to give you accurate insight into how long that function takes. But for most workloads, like 10 milliseconds is probably enough granularity to find like really bad performing code. So that's typically the default. And then for more local profiling tools, a pretty common standard is 1,000 hertz. So if you've used like Chrome DevTools or something, like most of those profilers run at 1,000 hertz. They collect 1,000 samples per second, and they will get you 1 millisecond granularity. So the sampling frequency does have an impact on overhead. So if I try and run PySpy with the default 100 hertz resolution, let's see what the overhead would be in this case. Oh, oops. Correct? Yeah, okay, this is good. So we're seeing 9% overhead from running PySpy with the default 100 hertz sampling frequency. So 9% is actually really good. You could comfortably run this in production without a significant impact on your application's production performance. And then what happens, let's see if we bump it up to 1,000. So you can see here with 1,000, you're looking at roughly 25% overhead. So the change is from 9% to 25%. So it's not a 10x increase in overhead just because you increase the number of samples by 10 times, but it is a significant jump. So those are some of the trade-offs involved. So you'll want to be careful about picking sampling versus deterministic. You'll want to be careful about picking a reasonable sampling frequency. And in most profilers, that sampling frequency is configurable, so you can choose a value that makes sense for the kind of code that you're trying to profile in production. But yeah, that was sort of like a short overview of Python profiling tools and visualizations and how they work. And so just finally, one thing I wanted to say, just kind of a brief mention of what Sentry's been doing in this space. So my team has been building out profiling at Sentry for about the last year and a half. We've been doing this in beta with a few thousand customers over the last year or so. And so we do have a production grade Python profiler and lots of tools to like view flame charts from production, aggregate data, kind of give you automated insights into the performance of your code. We're going to be at the Sentry booth answering questions and walking through demos and stuff. So if you're interested in learning more about this, just come stop by. And with that, I think I'll open the floor for any questions. And there's a mic in the center of the room if anyone has any questions.
I was wondering if there's any way to combine the data from multiple calls to this, so multiple files to create the same one flame chart.
Yeah, so if you were to take a flame chart and aggregate it to a single file, you can do that. What you would get is a flame graph, basically, because flame charts track duration, right? But aggregating durations is not typically useful. There's a lot of noise in those durations. So what ends up happening is you basically take the frequencies, how often the functions are called in each flame chart, and you aggregate them into a single flame graph. So when you look at a flame graph visualization from a typical continuous profiler, what that does is it runs the profiler on a bunch of different machines in the fleet across a bunch of different runs and dumps it into the same output. As for like how you would do that like manually, you could write a script to do it. There are probably scripts available already to sort of like merge flame chart data. But yeah, you would merge the flame charts into a flame graph, and then you do like a frequency analysis.
And the format that the cProfile or these profile tools use for the raw data, is that a Python-specific thing, or other languages have tooling that is compatible with it?
Yeah, so it is a Python-specific thing. So they have their own file format that it's dumped into. you are able to open the file format with pstats, and actually in Python 3.9, they added some additional APIs to extract the raw data from a pstats file. And so in theory, you could use those APIs to extract the raw data and output it into a format that is kind of more portable. So the Brendan Gregg flamegraph format or Speedscope or something, you could do the output. But the thing that's difficult about it is that you could only generate flame graph data from the cProfile data, because I mentioned there's this limitation where it doesn't capture like full call tree information. So, but yes, you could definitely dump the cProfile data into a flame graph manually by writing a little bit of code.
Thank you.
I might have missed, but how do you make such like a flame graph for like generators or like coroutines, which have like intermediate yield periods?
Yeah, so this is it's a complicated topic. Yeah, it kind of depends on your sort of concurrency mechanism. Like for example, our profiler does support some like greenlets to some extent. Async I/O is sort of a work in progress depending on how you use async I/O. So I would say that story is very much a work in progress. It'll work in some cases. So if we do like an all thread sort of capture in a profiler, you can probably see some of the additional threads that your workloads or your async workloads are running on, but you wouldn't really get like a really clean sort of like async stack trace. Like you wouldn't see a bunch of like async functions that are kind of ordered properly, like in the same flame chart and easy to parse. You would see work distributed across different threads. You kind of have to go and find that work happening on different threads. And so basically it's possible to get the data, but the user experience for actually analyzing it and kind of conceptually visualizing async stacks is difficult right now. So that's, yeah.
Yeah, thank you.
Just a quick question about the sampling window. So if the window is too big and there's a process that is smaller than the start and the end period, does that process not get captured?
Yeah, this is a really good question, actually. So yeah, you're exactly right. So it almost depends on the randomness of the profiler, right? Like let's say your function takes 1 millisecond and your window is 10, right? In most cases, that 1 millisecond function will start and stop in the middle of the window. And so your profile will never see it. On the rare occasion that the sampler lands exactly on the 1 millisecond mark where your function's still on the stack, then it'll get captured. So for a sampling profiler, if you're tracking frequency of functions, like kind of like statistically, if you're running this across like thousands of sessions, you'll get some data for it because you'll see it hit that mark occasionally, but it just won't hit it very frequently because of the size of the window. So it's not really like a reliable way of measuring it, but you will, in some cases with enough data, be able to see something.
And is there some like fundamental like minimum length that you've seen like throughout the different functions like within Python that, you know, like we don't want to sample too much, right? So is there some fundamental like smallest size that you've seen?
Yeah, so I don't know if there's like a fundamental one that I could describe, but in production, we typically use 10 milliseconds as the granularity. We find that most of our, so especially like in kind of like service level use cases, right? A lot of your workload is I/O bound. So you're often like tracing the call to some SDK that contacts AWS or GCP or your database or whatever. And those calls are often measured in the hundreds of milliseconds, not tens. So 10 milliseconds is perfectly like good enough for us to be measuring production workloads. But in the case where you have a CPU-bound workload where like, you know, optimizing every millisecond worth of performance is actually worth it, that's sort of the case where you would probably want to use a local profiling tool first with, say, like 1,000 hertz granularity, 1 millisecond, for those cases. But like I said, for typical sort of like Python server cases, 10 milliseconds is pretty sufficient.
This could be a question for the booth maybe, but is this Sentry Profiling new feature going to be in process or out of process?
Ours is in process. So our SDK ships an in-process profiler.
Hello, thanks for the talk. Just a question. Do you have any kind of automatic analysis tool for the profile or continuous analysis? Because as far as I know, you have to manually analyze them. So do you have anything like this?
Yeah, we do. So this is sort of one of the benefits of using like a cloud-based continuous profiling tool. So Sentry in particular will we'll collect a bunch of profiling data from production across sort of like different machines, different devices, and we'll run a bunch of aggregation. So one thing, for example, that we can tell you is we'll aggregate a ton of profiles, and then we'll show you your hottest code paths in terms of like function names. So we'll be like, we saw this function appear n times, and it's taking like roughly p75 of x milliseconds every time. And so here's a bunch of example profiles where this function is present that you can look at in more detail. Another thing that we do that is sort of a newer idea is, so we have like the Sentry error issues, which are generated whenever an exception or an error occurs. We're extending that concept to performance with profiling data. And so we'll automatically like take in the fire hose of profiling data, and we'll actually analyze for particular bad performance patterns. We have this for mobile as well. So for one example, on mobile, we have particular places where there's main thread code running on the UI thread that is expensive, like you're doing an image decode or a really large JSON decode. So we'll be able to flag that for you as an issue instead of you having to go through all the flame charts and find it yourself. We're also we're going to be extending that stuff to the back end. So that's the sort of like the more reactive use case instead of having to proactively go in and look at data.
Okay, cool. Thank you.
Great. I think we're done. Thanks, everybody. Really appreciate your time.